you and good time zone, everyone. We welcome you very warmly to our webinar on the value of direct air capture and storage. This is an IEAGHG hosted webinar, and I'm Jasmin Kemper. I'm the Technical Program Advisor at IEAGHG, and I will be your moderator for today. And our presenters will be Dr. Mai Bui from Supercritical and Dr. Nadine Moustafa from Imperial College London. And I'm now trying, but my slides do not forward. Apologies for that. Oh, there we are. It's just a lag. So the structure is we will first go through some welcome and housekeeping and a short introduction about the IEAGHG given by myself. And then Mai and Nadine will present you the results of our study. And afterwards, we will have a question and answer session. And so we'll kindly ask you to, during the presentation, to post your questions in the chat, and then I'm going to relay them to Mai and Nadine at the end. So who is the IEAGHG? We are an internationally recognized technology collaboration program founded under the IEA's Energy Technology Network. And we are functionally and legally autonomous, so all of our views, findings, and publications do not necessarily represent the views or policies of the IEA Secretariat or its individual member countries. And we are at the forefront of CCS research, and we pride ourselves to advance technology that reduces carbon emissions and accelerates the deployment of CCUS and CDR projects worldwide. Here on this slide, you can see our membership. So we have a mixed membership of governments and industrial sponsors, and those members fund our research and steer our research agenda. So since our inception, we have published more than 360 studies on a multitude of aspects relating to CCUS and more CDR as well. We also host some international research networks on costs, risk assessment and management, monitoring, modeling, and high temperature solid looping. We are also the guardians of some conference series, and at the forefront here is the GHGT conference series, where the next one will be in Perth, Australia in October next year, and also the post-combustion capture conference, which took place last month in Marseille in France. We are also hosting an international CCS summer school to make sure that young, educated CCS researchers benefit from networking and also can have an entry into a career in CCS. And so far, we have 766 alumni from more than 64 countries. And the last summer school, which takes place yearly, has taken place in Regina, Canada in July, and the next one is potentially taking place and hosted by INNO-CCUS in Denmark. We are also active in international regulatory developments, so we input into the UNFCCC, the IPCC, the London Convention, and the ISO TC 265. And we are also, as most of our reports are peer-reviewed, we are also giving back by peer-reviewing others' research, such as the IEA reports or activities by US DOE, US EPA, and CO2 CRC. And we also like to collaborate internationally with similar organizations such as the Carbon Sequestration Leadership Forum, the CCSA, the Zero Emissions Platform, GCCSI, the University of Texas, and we are hosting, for example, side events at the COPs with them, but also many others. So with this, I'm going to hand over to our speaker. So our speakers, Mai and Nadine, have delivered this study for our program. And Nadine is a research associate in the Chemical Engineering Department and the Center for Environmental Policy, specializing in systems modeling for carbon management and decarbonization technologies. And she's developing net zero strategies, including carbon accounting, policy, and carbon markets. And her work integrates socioeconomic and techno-economic aspects of various energy technologies, including CCS, CDR, nuclear power, and sustainable fuels. Nadine also served as the Program and Policy Officer at the Coalition for Negative Emissions. And together with Nadine, Mai will be presenting. Mai is the Director of Climate Science at Supercritical, a marketplace for high-quality carbon removal credits. Mai has over 14 years of research and consulting experience on CCS, clean energy, and CDR technologies, and has worked for Imperial College London, Innovate UK, CSIRO, and Monash University. And she was awarded the Junior Molten Medal in 2021 by the Institute of Chemical Engineers for her CCS research. And she's also been an advisory board member for Pure Earth, which is a VCM registry focused on engineered CDR pathways, and where she develops and contributes to the methodologies for CDR approaches. And Mai is also a member of the expert working group on carbon removals at the Science Based Targets Initiative. And Mai also regularly advises governments and contributes to the IPCC on the topic of CDR. So this was a whole lot of introductions. So now over to you, Nadine and Mai.
Great. Thank you so much. Yeah, that was very comprehensive. So hi, everyone. I'm Nadine, and today we'll be presenting our work in the report that was titled The Value of Direct Air Carbon Capture and Storage. So generally, we're increasingly recognizing that greenhouse gas removal is essential, not just for offsetting residual emissions, but for managing decentralized and historical emissions that can be mitigated through traditional means. Among the emerging different GGR technologies, direct air capture has gained a lot of attention. However, most of the existing work to date has focused on engineering DACCS systems. So as you see on the diagram on the left, generally people are looking at optimizing the reactors or estimating the costs or optimizing the materials associated with those technologies without necessarily looking at embedding these technologies into real-world energy systems. And so this study looks at DAC from a systems perspective, where energy availability, scale, siting, and permanence all fundamentally shape its value as a removal option. So next slide, please. So building on that systems perspective, this study in general evaluates the role of direct air capture, not as a single technology, but as part of an integrated decarbonization landscape. And so just to focus on specific things that are relatively mature and we can get the data for, we focused specifically on two technology families, liquid solvent-based and solid sorbent-based direct air capture. And we assess their performance across a set of system-level criteria. So we look at their carbon removal efficiency, we look at their timeliness, their durability, their land footprint, and techno-economics. And rather than projecting future uptake, this is more of a scenario-based comparative analysis grounded in literature reviews and specific energy systems assumptions. And so the aim is not to predict, but essentially to support strategic planning and investment decisions by essentially highlighting which factors are most influential and what kind of trade-offs exist in the real world when it comes to deploying this technology. Next slide, please. And so with this in mind, this is not a forecast and it's not a feasibility study. It's more directional and a comparative analysis. There are a few important limitations just to keep in mind when it comes to the study. And so one, and most importantly, this data is literature-based, which means it may not reflect latest commercial data. We also do not model dynamic grid interactions like marginal emissions or hourly dispatch. To ensure comparability, we model DAC as grid-connected, basically, infrastructure across energy mixes and regions. And so bespoke site-specific configurations. So for example, standalone DAC that's powered by renewables are out of scope. Or for example, waste heat integration is also out of scope. And broader sustainability metrics like local environmental or social co-benefits are not captured. And so, as I mentioned, those results should be interpreted as directional insights rather than precise quantitative forecasts. And for now, I'm going to pass on to Mai to go through all the results of this report.
Great. Yeah, thanks, Nadine. So the overall objective of this work was to essentially assess the value of direct air capture with carbon capture and storage, essentially. So understanding like the value of DAC and how it can be assessed. So first off, based on sort of what we know on sort of key criteria, one is the carbon removal efficiency. So how does accounting for things like the cradle to grave life cycle emissions, looking at both the embodied emissions of the infrastructure as well as the carbon intensity of the energy that's used, and how does that translate to the overall capture carbon removal efficiency of the process. We also looked at the timeliness. So if you have a process where you have embodied emissions, there's sort of a debt that has to be paid off. So if you build out your DAC infrastructure, how quickly can you then achieve removals? And we also look at energy system decarbonisation and look at those trajectories over time and how that will impact the timeliness of your DAC carbon removal potential. The third pillar is the durability. So we know that with carbon removal, permanence is really important, and the durability of that carbon that is stored away. So how long does that carbon need to be stored for in order to have climate benefit? So we look at this idea where you can use DAC for geological storage as well as potentially taking DAC CO2 and then making utilization products. And where is the trade-off there in terms of like how much should you store and how much can you use for CCU? And then the last pillar is looking at the understanding around cost and what the requirements might be in terms of also the land footprint and the techno-economics of a direct air capture system. And just to emphasize, this is done at a sort of global scale systems analysis. And so it is really, as Nadine said, it's like a thought experiment to show insights from a policy-driven type of perspective. So just to provide a bit more details on the efficiency side, I mentioned looking at the life cycle emissions was very much important, thinking about the infrastructure that's required and accounting for that in that carbon removal efficiency that is calculated. The other objective was to look at the timeliness. So we looked at global scale energy systems in different regional contexts, and then looking at these energy transitions based on some of the energy systems modeling that's been done by others to then understand, like, if you then deploy DAC under these different energy transition scenarios, what does that removal potential look like over time? And then the third objective was looking at the durability. And so we know that permanence is very much important. As I mentioned, we had the look at the trade-off between geological storage of that carbon versus utilizing that carbon to make various different products. And so we'll show some case studies to highlight what that trade-off looks like. And then the last objective was looking at the cost and thinking about how much and quantifying this and providing a bit more perspective around what that large system cost looks like. And so with the technologies, the two key ones at the time when we did the study, which actually was a while ago, there were two key technologies that we wanted to compare because at the time, the TRL of these two technologies were the most mature. But obviously, since this report, we first embarked on this study, there's been a lot more direct air capture technologies under development that have reached pilot scale. But at the time we started the study, the two that we looked at was the liquid-based direct air capture and then the solid sorbent-based direct air capture. So for the liquid-based, this is based on the technology initially published by the folks who developed carbon engineering. And so in this particular archetype, we know there is high temperature heating required. It's non-modular in nature, but then there's benefits of economies of scale with this sort of larger type of process, and individual plants will have larger carbon removal capacities of in the order of 1 million tons of removal per year. And then on the other side, we look at solid-based direct air capture, which is then requiring lower temperature heating. So it's only moderate temperature heating of about 100 degrees Celsius. It can use technologies like using moderate to deep vacuum. And then it is quite modular in nature. So individual units have small capacity. So these are the two technology archetypes that we considered and looked at comparing. And so in terms of the technical framework, we looked at deploying at a global scale. So the idea was we're starting at 2020 and we started a capacity of like 1 million tons of CO2 removal per year. And we scaled that up to about 1 gigatons of CO2 removal by 2050. And this was considering an S-curve type of approach to looking at logistic growth at a growth rate of 0.26 per year. And then we considered the cumulative emissions. So we looked at the LCA data for DAC for its value chains, looked at real world energy supply scenarios. We looked at the project change in atmospheric CO2 dynamically over time, and then considered like durability. The land footprint was also looked at. So we used data that had been published in literature to then try to provide some context around what that looks like at a larger system level scale. And then the last part was the techno-economics piece, where we looked at the CapEx, OpEx of DAC and trying to quantify the total system cost for the overall process. So the technical framework is quite flexible and it can be applied to various other direct air capture technologies as well, as long as there's the data around the techno-economics and the land footprint requirements. You could plug that into this sort of systems model to kind of get that picture. But as I said, like we chose 2 archetypes at the time, but obviously that could be, this model could be adapted to include other options if we've got sufficient data. So just to kind of summarize, we know with direct air capture processes, there is a life cycle consideration where you've got cradle to grave emissions that will happen over the lifetime and over the whole value chain of that process. So we needed to quantify this in order to calculate the carbon dioxide removal efficiency of the process as shown with this equation. And we accounted for the CO2 that's captured from air, but then also factoring in all the emissions required for the whole value chain. So this is the supply of the feedstocks, the material required for construction, also the carbon intensity of the energy that's supplied. And then if you use the CO2 to make utilization products, those products eventually re-emit the CO2 to atmosphere. So that also has to be factored in. And then whatever is essentially stored is then permanently stored geologically. So that's the full life cycle piece that we looked at and considered in this study. The scenario-based approach that Nadine mentioned also included looking at different regions of the world. And so we took data from from the inner database, inner data, where there were projections for carbon intensity of energy grids for 6 key regions. So we looked at the Pacific region, the Middle East, Asia, North America, Europe, and Latin America. And so the reason why this is important, as we know with direct air capture, as it utilizes energy, the carbon intensity of that energy can have a direct impact on the overall carbon removal efficiency of DAC. And so we've taken this projection over time from 2020 to 2050 to input into the model to then determine what that carbon removal capture efficiency looks like. So what we know in terms of the 2 processes, we've got the liquid-based DAC shown by the blue line, and then the solid solvent-based DAC shown by the orange line. So the carbon intensity shown on the x-axis and the carbon removal efficiency shown on the y. The carbon intensity of that energy must be low enough in order for it to achieve net negative emissions and overall carbon removal. And so if it is too high, we do result in net positive emissions. And that's why it's important to, when you're designing your direct air capture system, to access low carbon intensity electricity or energy. And so on the vertical lines, in the dotted lines, we just plot sort of like a point in time, the current energy intensity of Europe and then North America and Asia. And so obviously when you're looking at very high carbon intensity energy grids like Asia, you actually may not get net negative or net removal of your DACCS system. And so in parts like Europe, where the energy intensity of electricity is much, the carbon intensity of electricity is much lower, you will achieve removal. And so I mentioned the projection over time. So we took these profiles to the 2020 to 2050. So these high carbon intensity grids like Asia, the Middle East will actually decarbonize over time. And so using these scenarios of assuming that this trajectory of decarbonization occur, we can then show the performance of solid sorbent-based DAC and liquid-based DAC. So that's the orange is solid sorbents, and then the blue is the liquid base. And so what we see here is on the y-axis, the removal efficiency. So the positive numbers indicate that removal is occurring. So when you're operating in energy grids that are already quite low carbon intensity electricity, like in Europe, you can see that you're already doing removal and you get a positive carbon removal efficiency over time, and it just gets better as the energy becomes less carbon intensive. But when you look at the Middle East, where it starts off very carbon intensive, so Middle East and Asia, the energy grid starts at high carbon intensity. And then in these scenarios, the projection of integrating like low carbon energy sources like renewables and so forth will then start decarbonizing that electricity. And so then at a certain point in time, direct air capture will actually provide you net negative or carbon removal. And so that's just highlighting that certain parts of the world, whilst it might start off as not providing net negative, if we are focusing on decarbonizing of electricity, we can get there. And so this is why it underlies this very high priority that you're providing low carbon energy to your DAC systems. And as Nadine mentioned earlier, this is because we're assuming that we're using grid electricity, but obviously in a situation where you're looking at standalone DAC, which has its own dedicated source of energy, you can then pick and choose what carbon intensity is by dedicating that energy infrastructure for the DAC process. So on the piece on timeliness, so we looked again, this is a global scale model, just to remind everyone, and we're looking at deploying the DAC process and account for the life cycle emissions. And so here we looked at that carbon intensity, and then we also wanted to look at sort of like the worst case scenario and then also the best case scenario. So we looked at 3 different scenarios. So you'll see sort of a minimum bound and sort of minimum bound and upper bound, and then also like a solid line. So what this represents is there's the worst case scenario where the energy grid has no decarbonization after 2050. There's a scenario where it's net zero by 2100, and then the best case scenario is we become sort of net negative by 2100. And the reason why we wanted to look at this was just to think about like different scenarios where energy grids potentially could become net negative if you deploy technologies like DACCS or processes where the overall carbon intensity of that energy grid could potentially become net negative. So that's why we kind of wanted to see what these scenarios might, how that might impact DAC. So this is what you would see if you compare the liquid-based and then the solid sorbent-based DAC. So on the top there, liquid-based achieving slightly, it does achieve removals, but it's not as, you don't get as much carbon removal as, let's say, a solid sorbent, and that's due to those assumptions around the energy requirements, where because liquid-based DAC requires that higher temperature energy to regenerate the sorbent, that's why it kind of ends up being slightly less negative, slightly less negative. But overall, you can see sort of the minimum upper bound. So that's how you'll interpret the following graphs. And essentially what this is highlighting is global scale DAC can provide significant removals. And so overall, if you're looking at this sort of large scale systems level DAC, you could achieve in the order of like 35 to 50 gigatons of CO2 removal at a global scale. And then the other dimension that we looked at was the durability of direct air capture. And so this graph here is showing sort of the lifetime of various products that you can make as like CCU products. So you've got potential products that will have very different lifetimes. So if you geologically store that CO2, it is considered permanent removal. It traps that CO2 and locks it away. But you could take that CO2 and utilize it to make other carbon-based products that provide some sort of temporary sink for that removal, for that carbon. And then what is the implication of that in terms of like the climate impact or climate benefit? So let's say you make concrete, you take that CO2 and then make sort of like concrete or building materials, you would see like a product lifetime in the order of like 60 years, for instance. If you take that product and then make it into plastics for building applications, that might be a 40-year lifetime. And so taking this into account that there are different lifetimes, we wanted to see what the implication is if you factor that into your sort of CCU DACCS system. So here we've got different scenarios. If we assume the utilization product only stores that carbon for 1 year, that's the top left there. Then we see that over time between 2020 to here, we've projected it out to show that actually overall you're just emitting CO2. You're not going to get any removal over time. But as you look at more durable products that might have the carbon locked away for a bit longer, so let's say 10 years, 20 years, 30 years, 50 years, and then 100 years, you see very different trajectories. So at a certain point, if you really want to lock away that carbon, provide some sort of climate benefit, you need to be aiming for like higher durability materials. So let's say you're doing 50 years, you're still providing net negative by the 2100 year mark. But obviously, as we project out, those CO2, that CO2 will be re-emitted, and then overall by 2200, it does become net positive. So the whole overarching sort of message here is to show that even though you might want to utilize that CO2, if you do want a system that does provide carbon removal, you should be choosing products that have a longer product lifetime. But not to say that we haven't obviously factored in other aspects of this, where you can also consider, for instance, how you might displace the use of fossil fuels. This is pretty much just looking at the emissions of this DACCS system, but there will also be sort of co-benefits when you do utilization products where you're also displacing fossil emissions because you're not utilizing fossil sources anymore. But that hasn't been factored into this calculation. But that's pretty much showing that this whole message that I just mentioned there. So just to kind of then provide a bit more context, so that was just a sort of upper level looking at it purely based on the lifetime of the product, but then we also honed into specific use case scenarios. So let's say you take DACCS CO2 and you make methane, and you take that methane and you make electricity in a natural gas combined cycle power plant, and it's unabated. So that's scenario one. So we don't capture that CO2 from that natural gas utilization to make electricity. The second scenario is we take that DAC methane that's been produced, we put it into the NGCC, and then we do post-combustion capture. And in here, we assume 90% capture. So the third scenario is then another case where we take that CO2 from DAC and then we produce sustainable aviation fuel. So what does that look like from a systems level? And so we looked at this sort of trade-off. So what you're seeing on the x-axis is where 0 represents zero utilization. So you're not making any utilization products. You're just focusing on geological storage of your DAC process. And so you're getting a very net negative system. But then as you move from left to right, you start using a fraction of that CO2 to then do utilization products, so the methane and the sustainable aviation fuel, as I mentioned. So if we focus on just case study 1 with the methane DAC being used in an unabated NGCC, once you start kind of going, let's say at 50%, there is a scenario where the solid sorbent-based DAC is still like slightly net negative, and the liquid-based DAC, it is actually potentially in the worst case scenario net positive. So you're not actually doing any overall removal for the system. And then eventually at some point, if you were to take all that DAC CO2 to use in this process on this methane electricity system, you actually end up being net positive, which that's no surprise. That's kind of what we expected. But the surprising part was the second scenario for the case study. This was the only scenario that potentially could provide you actually a net negative system. So if you take that DAC methane and you put it into your NGCC and you captured that CO2 from the NGCC, you could actually overall utilize all that CO2, make methane, and then provide a system that does achieve net negative or net carbon removal. So that was quite interesting. And the key point here is that if you want to be at least net zero or net negative, some portion of that CO2 should be captured and stored geologically to offset the operational emissions. And that is indeed very important. And so there is a potential world where you could take DAC and make CCU products and still be net negative, but it's just looking at that correct proportion or the correct fraction that you use at this sort of systems level. And then the other piece was this sort of land footprint piece that we mentioned. And so here there's like different uses of land in a DAC system. One is the direct footprint, which is for the process equipment and the contactor spacing. And then the indirect footprint, which is really that part for providing resources like the electricity, the heating, and the water. And so that's like the sort of process showing here, the spacing that's required. So if you've got your contactor, there's some green spacing required, and then the red sort of the resources that would be needing to plug into your DAC system. So we compared the liquid-based and the solid solvent-based DAC, and often what we see is that the sort of process equipment, it does exist, it's just very small, which is why it's very hard to see in this graph. So process equipment doesn't actually contribute a significant proportion to that overall land footprint of your DAC system. But when you're looking at this sort of global scale deployment, the vast majority of your land footprint is actually associated with, in the worst case scenario, the resources required for the energy provision and utilities. And then also the spacing in between the contactors is also quite significant. In the liquid-based DAC, it is slightly high, like different in fraction. So the contact spacing is a bit higher, and that's just to do with the different efficiencies in those two processes. But ultimately, what we're seeing here is that you will need to kind of consider the sort of land footprint, and it can be important. And then also when you're thinking about systems planning, where do you locate and co-locate this equipment? But on that sort of bar chart, we could also translate this into like actual country level context. So this is an example we looked at, which was the UK, where they've set at a government level a target for specifically for direct air capture. So the UK government plans to deploy about 5 million tonnes per year of direct air capture by 2050. So what does that mean? And we showed by these little squares here, the worst case scenario on the right, and then the best case scenario here on the left. And that little tiny little pixel is associated with that 5 million tonnes of DAC requirement per year. And if you start thinking gigaton scale, then of course that's going to look a lot bigger. And so that's the sort of upper sort of boxes that show that. Again, the best case scenario on the left and the worst case scenario on the right. But ultimately, if you were to kind of do this, there will be multiple DAC plants. You're not going to do 5 million tonnes in one single site. It will actually probably be likely distributed because you actually need to plug this equipment into existing infrastructure. You need access to storage, access to the energy infrastructure. And so planning at a whole systems scale will be needed in order to make sure that you're effectively integrating this into your infrastructure. But in terms of like percentages, as you can see, it is very small in terms of the context of the overall UK land area. And so the last piece on sort of this techno-economic bit, we did a literature review. I refer you to the report for further details on that. But essentially what you can see here is the plotting of that literature data to show that, you know, for liquid-based DAC, the CapEx is lower when you compare that with solid solvent-based DAC. This is where, because the liquid-based DAC has higher productivity and actually benefits from economies of scale. So it actually requires sort of less process. It is a bit more efficient from a process equipment and CapEx investment perspective. And that's why you see a lower amount of CapEx requirement for the liquid-based DAC. But when you look at OpEx, the solid sorbent DAC is actually lower than liquid base, and this is due to the nature of the energy that's required. So you've got high quality energy required for liquid based DAC, where you're supplying temperatures as high as 900 degrees Celsius versus solid sorbent, which is low temperature heating and a little bit of electricity as well. And so ultimately in both technology cases, the highest proportion is attributed towards the carbon, the capex of the equipment rather than the opex. And so again, this is like a global systems analysis. And so we wanted to look at this. If you look at this at a global scale, what is this gonna cost us? And so we looked at the cumulative system costs. So if you were to try to deploy your 1 gigatons of CO2 removal capacity per year by 2100, this is going to cost quite a lot of money in terms of trillions of dollars. But when you actually compare this to the global GDP, it actually represents a very small fraction of the anticipated global GDP. So ultimately, if we are to achieve net zero and DACCS is to be a part of that net zero transition or net zero strategy, it actually, in the scheme of things, is a small part of a very small fraction of your global GDP. But what we actually see from this graph is like two key phases as you're deploying your DAC system. So the first part, in the early phases of DAC deployment, what you're seeing is the costs of DAC is actually being driven by your capex investment as that system expands out. And then in the later years and the later phase of deployment of DAC, it starts looking where it's driven by the OPEX and then also the CAPEX of replacing any retired or expired plants. And so I'll hand this over to Nadine to summarize the key recommendations from this analysis that we did.
Yeah, thank you. And so I think it was quite obvious that energy supply is the key determinant of DAC efficiency when it comes to all the results that Mai just presented. And so for DAC to achieve net negative emissions, it must be powered by very low carbon energy. And in our research, in our report, we found threshold carbon intensities of less than 0.21 kilograms CO2 equivalent per kilowatt hour for liquid DAC technologies and less than 0.45 for solid DAC technologies. In practical terms, this excludes most fossil-based grids today, unless combined with CCS. And so this is something definitely that we should be looking at. And then from a research perspective, this means LCA studies need to better reflect real-world energy mixes and not just idealized or generic assumptions, just to see where we'll actually land in the real world and whether we will be doing any sort of meaningful removal, as some of the results showed. And then from a policy perspective, grid decarbonization is not just helpful, obviously, for a lot of other reasons, but it's also a precondition to effective DAC. And you've seen that depending on where you are in the world, as the grid decarbonizes, you end up getting more meaningful and more positive, essentially, removal. That's on efficiency. On timeliness, the general recommendation is that it really, really matters. Our results show that DAC systems which ramp up slowly will struggle to achieve meaningful cumulative removals by mid-century, even if they perform well later on. And so given that our targets are net zero by 2050, it's something that we really need to consider. And that's essentially because the climate value of removals is front-loaded. Practically, that means supply chain bottlenecks and deployment constraints need to be tackled now, not later. And that's something that we need to really think about from a policy perspective. And for DAC to contribute globally, we need to start looking at expanding in regions beyond North America and Europe. And so looking at Asia and Middle East and see how they're going to be doing their energy decarbonization and what kind of ambitions do they have when it comes to delivering direct air capture globally. When it comes to durability, only geological storage guarantees permanence. Essentially, many CCU pathways offer short-term climate benefits, but result in eventual re-release of the CO2, often within years or decades. We highlight the value of CCS plus CCU DAC systems at a large scale. In general, where a portion of the captured carbon is utilized and the rest is stored. Essentially, what we show is that any deployment of direct air capture which achieves negative emissions, it must at least direct 40% of the captured carbon towards geological carbon sequestration. And in general, this helps reconcile the need for near-term revenue with the long-term need for durable removals. And so just to maintain integrity, at least 40% of that captured CO2 must be geologically sequestered for the system to remain net negative over time based on the results that we show in this report, given the scenario analysis that we do. From a land perspective, DAC is often perceived as land intensive. But when compared to other removal options, its footprint can be relatively low. For example, BECCS and reforestation, afforestation, especially per ton of CO2 removed. And so, however, as we've shown, this kind of really depends on siting and energy usage. And so high energy DAC systems would need more land, for example, for solar panels or wind, and that's something that we need to kind of consider. And so this study did not look at co-locating DAC with waste heat or siting infrastructure, because that can reduce the land and is definitely a key research area that we need to look into. And so looking at what kind of scope and where should we be siting our DAC systems, and citing, for example, whether we should be looking at things between air contactors, a strategy to reduce land footprint. All of that is a key research area that we need to look into, and it's not something that we could cover in the report, given that there's not a lot of data out there on it, and because we wanted to maintain the comparability of the different infrastructure. The different grid power. And so that said, DAC deployment will inevitably be distributed, and so long-term infrastructure planning is essential to avoid bottlenecks. And that's a lot of what we try to show in this report is that we're modeling the scenario analysis. We're looking at what kind of things are quite important from a trade-off perspective or from an influential perspective. And this is one of the things that definitely came up, where we really, really need to start looking at and thinking about the infrastructure that we require for DAC. From a techno-economics perspective, on a research side, we really need standardized techno-economic methods to reduce the uncertainty in the reported costs, more data out there on this, and looking at modular plant designs to support mass manufacturing and then drive down the capital expenditure. From a policy perspective, high upfront costs remain a major hurdle. And so this is generally, in current markets, it's generally not enough to cover early stage marginal costs. And so with that public support, DAC will have a harder time scaling up in the near term. And then long term, with the right investment, hopefully costs could fall, but we really need the market formation mechanisms to unlock that trajectory. And note that what we said about timeliness, that we need to do this sooner rather than later. And finally, just want to say that building on that systems perspective, the study evaluates the role of direct air capture, not as a single technology, but as part of an integrated decarbonization landscape. And so as we talked about, we focused specifically on the two technology families. So we looked at liquid DAC and solid sorbent DAC. And we assessed their performance across a set of system-level criteria, so their carbon removal efficiency, the timeliness, durability, the land footprint, and techno-economics. As we mentioned several times, this is not projecting future uptake, but instead it's a scenario-based comparative analysis, and it's grounded in literature and the energy system assumptions. But in general, it kind of starts asking the questions of asking and answering the questions of under what conditions would DAC provide genuine large-scale net removals, and what kind of constraints, whether it's technical or spatial or economic, would shape its system-wide value. And so to ensure comparability, we modeled it as DAC that's grid connected across the different energy mixes and regions. And so ultimately, this work provides a system-level view of DACCS that moves beyond the technical potential So essentially looking at it from a very improving the reaction mechanisms, for example, or improving the reactor itself. But instead, it assesses when, where, and how it can contribute meaningfully to climate targets, highlighting the most influential parameters and real-world deployment trade-offs that we really need to consider to start looking to basically start getting to our net zero targets. Thank you so much, and I think we're open for questions. There's quite a few questions already on the chat. I don't know if you can see them, but I can.
Yes, thank you, Nadine and Mai, for this comprehensive presentation. And yes, we indeed have a couple of questions in the chat. So the first question is, Mai, as you mentioned in your 2022 paper, DACCS systems are highly sensitive to climate conditions. And in your current work, are the reported net efficiencies cumulative removals calculated by taking into account the local climate conditions, region and time period where the analysis was conducted?
So this particular work didn't account for that, but we do recognize it as an important feature just because it was this sort of like high level global system scale model and also quite a simplified model. So we couldn't actually go to that level of rigor. But yeah, that's definitely something that's been done in follow-up work in the papers for One Earth, and then we did a subsequent one where we looked at specific energy systems that were integrated, and we used that sort of high resolution model. But I'm happy to direct folks to that particular paper if they are genuinely interested. But yeah, this was very much just a systems level analysis, which doesn't account for that climate impact that was very much shown to be very important.
Yes, maybe I should say to the defense, our scope from our side didn't include that because we noticed that there's still a lot of work focusing very much on the techno-economics, on the costs, and we wanted to go one step further, but we, of course, could not cover everything, and such as the ambient variability and also water footprint we could not cover in this study, but we will also try to cover this in future study, as well as comparison with other now also relatively more mature DACCS technologies. Then there is another question on that the approach is highly reliant on the regional grid's future projection of carbon intensity. And if you could please explain the basis for the evolution of the carbon intensity in Latin America. Is this because there is more solar, more wind, or more renewable fuels being used? Do you have any insight on why exactly, what will exactly happen to it?
Yeah, so in these particular energy system models, like we didn't actually do that modeling ourselves. We did there was a secondary data source that we were using, but in that work, they did assume that as you sort of integrate more renewable energy, that's what leads to that sort of decarbonization of the energy grid. But they kind of base it on certain assumptions around that particular region. So there will be potential renewables, but then also other low carbon intensity energy sources could be nuclear and other options that I can refer folks to that particular modeling work if they want to see the exact assumptions. Like I can't remember with Latin America whether it was just renewables or whether, and I suspect it was mainly just renewables that was being integrated that led to the carbon intensity reduction, because that's kind of where majority of the reductions in carbon intensity was being achieved. Yeah, and certainly in some countries that do more nuclear, they might have used that, but I think there's been sort of a trend where they have moved away from nuclear, as we see in Germany, for example, and certain countries just assume no nuclear being deployed because it's just from a public acceptance point of view, it's very much limited. So majority of the decarbonization is really much achieved through renewables.
All right, then a question on the case studies. The question is, would you not need to compare these results to another case in which you would use hydrogen for direct electricity production and combine that with DAC and CCS, and whether that would be a more effective route as it wouldn't include the relative inefficiency of producing methane from CO2?
Yeah, that is a great point. Due to the limited time and the scope of the study, we couldn't do obviously all of those particular scenarios, but it's a great point that the hydrogen scenario would be an interesting comparison point as well. But in this particular case, we didn't factor in the carbon, the sort of energy requirement of the hydrogen that was used, I don't believe. So that's more or less, yeah, just looking in isolation just on the DAC and the CCS. But I think that particular question was asking to look at a pure hydrogen case. Is that right?
Yes, as far as I understood, yeah.
Yeah, so like a hydrogen CCGT plant, for example. I think there was one particular paper we had done in the past where we did compare DAC to methane and then DAC, and then also looking at a hydrogen CCGT to compare the energy and then the carbon intensity for those different scenarios. That wasn't part of this particular work, but there is a previous paper that we had actually done hydrogen CCGT to compare against DAC methane CCGT. So that's something I can refer that particular audience member to if they want to kind of see that. And in that particular paper, we were looking at this in the context of also energy storage. So if you're storing methane versus storing hydrogen, I think ultimately it showed that the methane case was still better overall from an efficiency perspective, because when you look at round trip efficiency, the hydrogen case actually didn't look as good.
Okay, then there's another. Could you comment on the parallel for temporal correlation between hydrogen and DACCS in a broader policy context? Trying to follow up on the.
Is that, oh, this is the last question.
Last question, yeah.
Parallel.
I'll just skip over the one first and we go back to the other one. Yeah. But
Yeah,
maybe that one
that's
first.
I think that's a great question. So ultimately, with policy, you can kind of see like certainly the way we do things is quite siloed. So there's not really like an approach where we go, here is the DAC deployment and here is it the hydrogen deployment strategy, and then trying to kind of synchronize those in a way that kind of thinks about that in a sort of temporal manner. And that's quite unfortunate because there probably needs a bit of temporal correlation between that infrastructure deployment, because if you want to do CCU, you need both low carbon hydrogen as well as that CO2, sustainable CO2, to kind of do these sustainable products like fuels and so forth. And I think that's from a government perspective with policy development, is that if you do want to do CCU as part of your strategy, that sort of dual prong approach of thinking both how do you deploy the hydrogen infrastructure alongside your CCS infrastructure is actually needed. So we kind of emphasize that point multiple times, is this whole idea of like integrated systems planning being needed. And that includes not just the DAC and CDR infrastructure and the energy infrastructure, but also thinking about hydrogen infrastructure if you're thinking CCU.
Yeah,
Did you have anything to add, Nadine, on that point?
Not on the hydrogen, or could we?
No, sorry, I completely agree. I think everything we do is quite siloed rather than iterative, for example, or interdisciplinary. But I do see that it's becoming more of a thing, at least from a research perspective. So people are slightly less inclined to just work on their specific technology in silo, and instead looking at, what else is out there. How can, for example, if you look at nuclear power in the UK, it's one of those things that now they're looking at making it more of an energy hub rather than a nuclear power station. Where they want to start looking at essentially producing sustainable fuels and also doing DACCS within the boundary of this nuclear power station, and not just focus on producing nuclear power. So it's something that you're seeing more and more of, which is good, but I wouldn't, like, a lot of the policy that we talk about from a policy context perspective, it's done pretty much in silo, but at least you see that in research, it's something that people are looking into, and it seems like an industry that's also something that people are starting to notice.
Yeah, and that point kind of touches on the new question that we have about this idea around this particular infrastructure will be, large machines that are huge and will look imposing. And so from a sort of like public acceptance piece, there could be some issues around that. And I guess the energy hubs is one interesting idea, Nadine, that like, kind of localizing and building in an area where they've already kind of quite accustomed to seeing industrial infrastructure, then public acceptance might be better in those regions of the world. And in the UK, they do have these key sort of industrial clusters that they're looking to decarbonize, and that is where particularly the access to CO2 storage will be, but then you're also in regions of the UK where they will be accustomed to seeing industrial infrastructure. So deploying DAC in those regions, the public acceptance might be better. But in other parts of the world, it will be very different, where if you're trying to deploy DAC, and that idea of doing DAC anywhere and it being, deployed anywhere is probably not true when you start thinking about it from the constraints around available infrastructure, but also the public acceptance piece. So in certain parts of the world, they may be less approval. There will be less approval for DAC where they're not used to or accustomed to seeing that type of chemical type of equipment.
Yes, thank you. And then we skipped one which we can come back to, and someone's asking that it would be interesting to have a land area comparison against solar, because solar is also proving more and more controversial. So because it might potentially lead to the loss of productive farmland, and how DACCS might be an alternative option.
Yeah, that's actually something we looked into in the paper that one of the earlier questions mentioned was the One Earth paper. We did a follow-up study where we did sort of geospatial modeling of DAC deployment, and we considered different energy inputs. And so we looked at solar versus doing like natural gas combined cycle with CCS, and then nuclear, and then various other options to see which case, what's the land footprint look like. And then in the solar case, obviously it did use a lot more land. And in that paper, we also proposed ideas where you could multiple uses of that land. So for instance, there was proposals where you might have your solar field, but you could do, sort of cows or cattle grazing in between. And so maybe it's like dual use of that land. So then it's more efficient use of that land rather than just thinking of it just dedicated to DAC. But that particular paper actually quantifies land footprints, looking at these sort of regional contexts, and it does account for those climate impacts that one of the first questioners asked about, and also the specific dedicated energy inputs for DAC. And so unfortunately, this particular study, this was out of the scope because of the time constraints that we had.
Yeah, thank you, Mai. I think those were all the questions from the chat. If someone still has one question, I think we could deal with one more. If not, then maybe worth mentioning. So I will put it in the chat in a second. So our reports are available on our website, and if you live in a member country or if you are from one of our industrial sponsors, then you have immediate access. Our reports usually have around a 6-month holding period until they all go public. And if you need any help accessing any reports, then please feel free to reach out to our communications manager, Tim Wilson, who will be able to help you if you want to access specific reports but haven't have an account yet or so. And maybe Mai and Nadine, the papers you mentioned, if you would like to also drop the links here, I think attendees can still see if something's being posted in the chat, and then they can also follow up those pieces of research from here. And then, the only things left for me is to thank everyone for attending this webinar, and thank you for all the questions. Of course, thank you, Mai and Nadine, for presenting this piece of work. Also, thank you to our comms manager for helping me organizing this webinar. And I wish you have a pleasant rest of the day, and hopefully see you in one of our next webinars. Bye.
Bye. Thanks, everyone.